Okay, seems like we have quorum, so I'll get started. So this lecture is going to finish up the section on policy gradients, and I'm going to talk about a different class of policy gradient estimators, where instead of taking a bunch of actions and then either increasing or decreasing their probabilities, these methods have a different interpretation as actually computing a gradient through a value function and using that to update the action. Or basically pulling the action towards a better action, as opposed to trying to increase or decrease its probability. So that'll make more sense a little bit later. But before I go into the details of how to use this idea in reinforcement learning, I want to just talk more generally about estimating gradients of expectations and why it's possible that there are two different ways of estimating these gradients. And this is actually something that comes up in a lot of different parts of machine learning and even other, probably other branches of engineering also, where you have so you have two different, we're going to show that they're, oh yeah, so you might have heard of variational autoencoders with the reparameterization trick. So that's sort of another case of this idea. But anyway, just to set up the problem, let's say we have an objective function f, and we have a random variable x, and our objective is expectation of f of x. And x is sampled from some parameterized probability distribution, which we have control over. So we have this probability mass function p, which has parameter theta, and this is something we have access over. We're defining this so we know the gradients and the values of this probability mass function. So the question is, we want to compute the gradient of this expectation. And since it's not assumed, it's assumed that we don't have access to f. So we don't have f, and so don't know f. And so the problem is we're just treating f like a black box, but we want to compute this gradient of an expectation. And we talked previously about the score function gradient estimator. So what we introduced in about a month ago when we talked about policy gradients for the first time is we showed that this is equal to a certain expectation. So this gradient of the expectation can be written as an expectation of a gradient. So here we have expectation of grad log probability. Whoops, this is just not a policy. Probability of x times f of x. And since we wrote the gradient of an expectation as an expectation of a gradient, now we can just collect a bunch of samples of x and obtain an unbiased estimator of this expectation. So this is a way of computing the gradient by Monte Carlo. We just get a bunch of samples of this inner quantity. So that's one way of doing it, but there's also another way of doing it. So let's say x is a real number or a vector of real numbers, and p is a probability density function. Then in general, in non-pathological conditions, we can redefine this process in a different way, where we say we first sample a random variable z from fixed distribution. And then we define x as some deterministic function of theta and z. So, and this is what you do numerically. If you're actually writing a computer program to sample from some probability distribution, what you do is you sample from some fixed distribution, such as uniform numbers, and then you transform it by applying a certain function to get the distribution of interest. So in particular, what you're going to use is the inverse cumulative density function. And if you plug in a number between 0 and 1 into the inverse CDF, then it outputs a sample from the distribution. So for example, for that, yeah, that's how you can sample from any continuous distribution in one dimension. And you can do something very similar in the multidimensional case, where you just sample one component at a time using this method. But for the purposes of this, this discussion, let's just pretend we have a one-dimensional random variable, because that makes it a little simpler to think about. So here, x and z are going to be real numbers. So we said that you can, instead of just thinking of x as a sample from a probability distribution, we can sample from some fixed distribution z, which does not depend on theta, and then transform it. Well, then x is just defined as a deterministic function of our parameter theta and our z, which is like our random seed. So then now we just have expectation over z of x of theta z, and we're taking the gradient of that. So under appropriate conditions of differentiability, we can just swap the gradient and the expectation. So this is under appropriate analytic conditions. We can't do this. It turns out we can't do this if, whoops, we have f of x. We can't do this if f is discontinuous. Actually, it's OK if f is non-differentiable. It's just bad if f is discontinuous. And I'll show you a picture that'll give you intuition for that. But so if f is continuous, we can just swap the gradient and the expectation and say we have the gradient of f of x of theta z. So let me just give you a little intuition of why this doesn't work when f is discontinuous. Or actually, when this whole function, f of x of theta comma z, this has to be continuous. This can't be discontinuous in theta, or else we're in trouble. So just to show you that, let's say f of x is the step function. X is just, so we have the x-axis is just x. F of x is the step function. So if we, and let's say theta is the mean of a Gaussian distribution. And let's say x is the sample from the Gaussian distribution. So let's say here we have theta is the mean, and then we're going to sample from this Gaussian. And then f of x, we apply this step function. And this gradient, if we look at this expression for the gradient estimator, it says that you just look at the derivative of, this whole expression. I mean, but we can expand this out with the chain rule to get gradient of f applied at x times x d by d theta of x of theta z, right? So we're just doing the chain rule here. And so we have this. So you can see that we're just, oh, whoops, this should say f prime of x times the derivative with respect to, oh, you can't see that? OK. OK, so in our expression right here, we can just expand. I'm just saying we expand it out with the chain rule, so we get f prime of x times d by d theta of f of theta z, right? But the problem is f prime of x is 0 everywhere for this step function, except it's a delta function at the point where it goes up. So we're always, if we actually collect a sample from this distribution and then we plug it into this expression, we're always going to get 0 because the derivative of the step function is 0 everywhere. So that's no good. So it's clearly, this isn't going to work if f is discontinuous. It turns out it works, it's correct if x is merely non-differentiable. So that's, this is called the pathwise derivative estimator. So, and it's often, if you have the same expectation, you can compute two different estimators, which both can be, you can estimate both of them with Monte Carlo. And you just have to reparameterize the sampling process to get these two estimators. So that's the main point. And there are different conditions under which you can use these two estimators. So as we described before when we introduced the score function estimator, that is valid even if f is discontinuous. So if f is discontinuous, you can use the score function estimator, but not the pathwise derivative. And same thing. If x is from a discrete set, you can use the score function estimator, but not the pathwise derivative. So it's a little more flexible. On the other hand, as we'll show very shortly, it tends to have much higher variance. So if you can use the pathwise derivative estimator, you want to use it. It's called the pathwise derivative estimator because you can, one way you can think about it is, in this estimator, you're looking at, if I wiggle theta a little bit, how much does x wiggle? And then how much, in turn, does f wiggle? So it's like you're looking at how the path changes. If you look at your set of samples as forming, your set of random variables as forming some path, you're looking at how much the path changes when you change your parameter. Whereas in the score function method, you're freezing the whole path, or you're freezing the values of all your samples, and you're just looking at how the probability changes. So these are the two estimators. Can anyone think of another way of estimating this same gradient that's different from both of these two methods I introduced? Yeah, that's right. So another way to do it is just do finite differences on theta. So let's just briefly consider what that would look like. I'll erase the score function part. And actually, the reason it'll be useful to look at this is because it turns out to be very similar to the score function estimator. So the finite difference estimator, the way that would look is, again, we're going to use the same reparameterization we used for the pathwise derivative. So we're going to say we have a deterministic function, x of theta z, and we're taking some loss. We're applying our loss to that value. So for finite differences, we're going to evaluate theta plus, let's just call it e sub I, which means it's a one-hot vector with a 1 in the ith location, in the ith component, and let's multiply it by sigma, which is just a scalar. So we have theta plus. Actually, let's just say this is a one-dimensional problem. So we don't have to worry about the one-hot vectors. But for now, so let's just say we want to evaluate it at theta plus sigma and theta minus sigma. Then our finite difference estimator is just going to be f of x of theta plus sigma z and minus f of x of theta minus sigma z over 2 sigma, right? OK, so that's yet another estimator we can use. Yeah.
There on the top, you meant x, no? F prime x and then like.
Oh, let's see. Oh, sorry. Yeah, that's correct. Yeah. Yeah. OK, so here's our finite difference estimator. So now I'll show that this is actually kind of similar to the score function estimator in the case that we're using a Gaussian distribution. So in the case of a Gaussian distribution, we're going to first sample a normal from a normal distribution. So let's say z is our normal random variable. And then we're going to just define x equals some mean mu plus sigma times z. But for now, let's say that our parameter is we're parameterizing the mean of this distribution, and we're not trying to learn the standard deviation. We're just trying to learn the mean. So our mean is going to be theta. And now let's just look at what the score function estimator tells us. So the score function estimator is just grad log probability of x times f of x. So in the normal distribution, probability of x is just exponential of negative x minus the mean squared over 2 sigma squared times, and this is all over square root of 2 pi sigma squared. So if we take the log probability and then we take the grad log probability, I'm going to run out of space, so I'll start writing over here. So we take the grad log probability. We don't care about this denominator, so we have grad with respect to theta of the thing inside of the exponent, so negative x minus theta squared over 2 sigma squared. So then we get, and then this is times f of x. So just taking the gradient of this expression, we get x minus theta times x minus theta over sigma squared times f of x. So let's see. See, did I miss something? OK, no, this is right. And then just using our definition of x is theta plus sigma z, we get sigma z over theta squared times f of theta plus sigma z. And so we end up with f of theta plus sigma z times z. So that's our estimator. So we take a little step in the, we take a normal random variable z, we multiply it by some scaling factor sigma, and then we take a step in the direction, we multiply that by z to get our gradient estimator. And so the interpretation is, let's say z is positive. So let's say you're taking a little perturbation in the positive x direction. Then if the function value increases, then the gradient is probably positive. Or then you should probably move in that direction if you're trying to maximize f. But OK, so this still doesn't look like our finite difference expression, which is this, right? But now now there's a well-known trick in statistics or in Monte Carlo estimation called antithetic sampling, where if you have a distribution that's symmetric, you can collect pairs of samples instead of single samples. So let's say we have a Gaussian distribution like this. We can collect one sample from the Gaussian, or we can, if the distribution is symmetric, we can compute the same expectation by getting both a sample and its mirror image at the same time and averaging them. So let's say we do antithetic sampling. Then we're going to take f of theta plus sigma z plus f of, and that's times z, plus f of theta minus sigma z, and that's times negative z. So then we, and sorry, this was over sigma squared, over sigma. I forgot the sigma in the denominator. So now, and this is all over sigma. And then we also have to divide by 2 because we're doing 2 samples and averaging them. So then when you write this out, you get the, let's see. Is this right? Oh, OK, yeah. So we have z over sigma times f of theta plus sigma z minus f of theta minus sigma z over 2 sigma. Let's see. Something is a little wrong. Wait. We have a z in front of here. OK. So it's not exactly the same, but it looks pretty similar. So if we imagine, for our antithetic sampling, we can sample where z is always positive because we're taking the sample and its mirror image. So all z is introducing here is it's a random scaling of our step. So anyway, I'm not telling you that it's exactly the same. It's not exactly the same. If you can do a Taylor expansion, and then you'll see that the score function gives you the you can see a little bit more exactly what the score function is doing in the if sigma is small. But you can see that it looks pretty similar. So, oops, I can't show you both at the same time. So here's the finite difference where you have you're taking the difference and dividing it by the step. And here's the score function gradient estimator, where you're sampling from a Gaussian distribution and then applying the using the score function estimator. So these two things are very similar. And one thing you can take from that is that when you use the score function estimator, which is what we do with policy gradients, you're actually doing something very much like finite differences. So in policy gradient methods, you're sampling a random set of actions, and then you're doing the score function estimator. That's kind of like doing finite differences in action space, or in the space of action sequences. This is a kind of hand-wavy argument, but in effect, that's sort of what you're doing. Does that make sense to people, or does this not make any sense? I mean, I showed you just the 1D case, so you can think about the n-dimensional case, and you'll find that you end up with, well, z is the same calculation holds, but z is a vector. So you end up just taking the difference in function values. You're taking like a directional derivative and multiplying it by the direction. So this is, yeah, so that's in the multidimensional case, you're doing this random direction. You're computing the derivative in a random direction. And it's like random direction finite differences. So that's sort of pretty analogous to what you're doing when you do a policy gradient method, except in trajectory space. OK, so that's just the review of gradient estimators. So we've got the score function, we've got the pathwise derivative, and we've got finite differences. So now I'm going to talk about using the pathwise derivative type estimators in the reinforcement learning context. So here, let's just look at the process you use for sampling all the states and actions in an episodic MDP. So we have our parameter, our policy parameter theta, and we have our states and actions. And let's just say, for simplicity, that the reward is computed at the very last time step. And we want to compute the gradient of the expected reward. And the way this calculation works is you end up taking the grad log probability of the actions along the trajectory. So that's how our policy gradients usually work. So now let's look at how we can reparameterize it more like the pathwise derivative estimation method. So let's say now we try to do that trick I just showed you, where we say, now we're going to sample a random variable z from some fixed distribution, and we're going to define the policy to be some deterministic function that takes in the policy parameter, the current state, and the noise. So can we do a policy gradient that way? So now I've redrawn the graph a little bit. So squares mean random variables that are sampled from some probability. Circles mean samples from a probability distribution. And squares mean deterministic functions of their parents. So now this is the new graph. And we're going to change theta. And that's going to actually, if we perturb theta, that's going to change the action. So we're considering this to be a deterministic function. So the problem is that this only works if our transition model is known. And the problem is, if we try to take a derivative, if we write down the gradient estimator for this expectation, for example, if we just write it down as a big integral, that's a way of doing this calculation, then what we're going to end up with is we're going to end up with ds2 by da1 if we expand out all the chain rules, because the dependence on theta propagates through these two steps, these two functions. So that's our problem here. I mean, in MDPs, we don't assume that we know what the dynamics model is. Actually, if we did know the dynamics model and if it were continuous, then we could do this estimator. We could do it this way. But if not, or actually, if we, actually, I said the wrong thing. It doesn't have to be a continuous, S2 doesn't have to be a continuous function of S1 and A1. We just have to know the transition probabilities. So if we know the transition probabilities, we can actually use this kind of estimator. If not, we can't. Any questions? Okay. Okay. So we're stuck briefly, but function approximation comes to the rescue. So what we can do instead is, instead of trying to estimate the dynamics model or use a known dynamics model, we can estimate a Q function, and that's going to allow us to compute this gradient. So this is actually, we have to do a pretty simple chain rule calculation here. So we want to get the gradient of the expectation of the final reward. So just using the chain rule, we can say that the dependence on theta, theta only affects the result through its effect on all the actions, because if we change theta, it's the only variables it directly affects are the actions. So this is a valid. This is just using the chain rule to write down the gradient with respect to theta in terms of the gradient with respect to the actions. So now, so we can break it down into this sum of derivatives with respect to the actions, and here we have the expectation of the reward given the teeth action, and this expression right here is just the state action value function. It's the Q function. So here we can just write this as a sum of the as a sum of gradient of the Q function, or derivative of the Q function times the derivative of the action with respect to the parameter. And finally we can pull it out. So I mean, we can pull the derivative. I mean, we can pull this into one expression, Q, where we take the Q function of the state and then the action directly. And I mean, this is just applying the chain rule again, but in reverse. Does anyone have questions about any of these steps? This one, I mean, this step, there's some caveats to this step because you have to make some assumption. You have to basically assume that all the noise is frozen. Otherwise, it doesn't make sense to say derivative of R with respect to action. So if we assume that all the noise is frozen and everything is differentiable, then this expression makes sense. And then here we're just pulling in the expectation with respect to all variables that get sampled after A sub t. So this is just like moving around the expectations, or moving the expectations through the derivative. So the idea here, and this algorithm is called the stochastic value gradient algorithm. So you're learning continuous control policies by stochastic value gradients. They derive it a little differently. So if you're interested, you can also check out their derivation. So what you do is you learn a parameterized Q function to approximate your discounted, your true discounted Q function. And what you do is it just looks like a batch, or it looks like a policy optimization method, a typical policy optimization method. You run your policy to collect some time steps of data. Then you compute the gradient of your loss function, which is just the Q function applied to state, and then the action, which is a deterministic function of everything. So you can see here that this is just a nice big loss function that you can differentiate. So this is pretty easy to implement. And then you just update it. Then you just take a gradient step. Sorry. You use that gradient step to update the policy, and then you also try to update your Q function to be more accurate. So that means you use some estimator of the returns, and you just set up a squared error loss, and you take a gradient step on the squared error loss. And you can use you can use lots of different ways of estimating the target Q function. For example, TD lambda.
Is it going to take a long time for this to converge?
That's going to depend on the problem, but I would say if the conditions are right, this has much lower variance than the score function gradient estimator. Actually, let me make one thing that I should say about about the estimators that I just talked about, the score function gradient estimator and the pathwise derivative estimator, is that under most conditions, the pathwise derivative estimator has much lower variance. So the reason for that is, let's say our function f is linear. Then it's going to have, I'll come back to that later. I don't want to get bogged down there. So I'll finish up this section, and then I'll talk about the variance of the estimators. But anyway, this is the stochastic value gradient algorithm. That's not the only possible thing you could do. So this paper describes a bunch of other variations on the idea, where the theme is that you're differentiating through the you're not computing gradients of probabilities. You're computing gradients of the path of different segments of the trajectory. So there are different choices. I mean, one of the choices is and they call this one SVG1, is instead of learning a Q function, you learn a state value function, and you learn a dynamics model. And that's, I mean, with a state value function and a dynamics model, you can approximate the Q function, or you can define the Q function in terms of these two things, because you just take next state next state and then value applied to the next state. So you can define the Q function this way, and so one really nice idea here is that let's say you have a trajectory. The problem is your dynamics model might not generate that trajectory. Your dynamics model is going to be wrong, so it's going to predict different transitions than the ones you actually see. So you see state action next state. Those are the ones you actually measure, but then your dynamics model might predict a different next state. So what you can do is you can just say that whatever error you saw is just the noise. So you can say that the dynamics model is a little noisy. In this case, we have some additive noise. And what we're going to do is collect a trajectory, then assume that all of the errors or the mismatch between our model and the actual trajectory was just the Gaussian noise. And then we freeze the noise, and we compute the gradient, assuming that all that noise was fixed, and using our dynamics model to compute the gradient. So if we look at this graph, I think I have another. Do I have another graph? OK, no, not quite. OK, so I see. OK, so here's the here's what we do with the here's what we do where we just rewrite the Q function in terms of the value function and the dynamics model. So that was what I talked about just a moment ago. And as I said, you infer the noise by just assuming that all the mismatch between your model and the real data was just the noise. And the other idea is you don't even need a value function. So you can just learn a dynamics model and differentiate through the whole path instead of just looking at a one-step rollout. So I mean, if you look at this expression, we just look one step ahead in time. So we run our dynamics model for one time step to get the next state, and then this is our expression for the value. I mean, this is our expression for the next state, and we plug that into the value function. So this expression here that we're putting inside this expression here for our Q function is just it's just using a one-step look ahead using our dynamics model, but we're never running our policy for more than one time step. I mean, we're never using our dynamics model for more than one time step. So what we can do instead is we can differentiate through the whole the entire deterministic computation graph. So we learned this dynamics model. Now we assume that now we know both the policy is a deterministic function and the dynamics model is also a deterministic function. So now we just have a nice big deterministic computation graph like an RNN, and we can just differentiate the loss function through the whole thing. Just do back propagation from the reward back to our parameters. So that's another approach, and this is called the SVG infinity algorithm. So they applied this to some 2D robotics tasks, and what they found is that all of the gradient, they found that they did get a pretty decent improvement with one of their variants of the algorithm, where they also add in experience replay. Though without experience replay, all of the methods were pretty similar. That means using the SVG0 and SVG1 were pretty similar. That's whether you parameterize the Q function or whether you try to learn the Q function or you learn the value function in dynamics model. And OK, so now that's the stochastic value gradient algorithm. Then there's this other algorithm, the deterministic policy gradient algorithm, which was actually proposed before the stochastic value gradient algorithm, but it turns out to, well, it's sort of a special case and a limiting case of the stochastic value gradient algorithm. So that's why I am introducing it second. So actually, the original motivation for the deterministic policy gradient algorithm was that the variance of the score function policy gradient estimator goes to infinity as the variance goes to 0. So let's just look at why that's true. And actually, here's a good time to talk about variance a little bit. Could I have the lights on the board, please? Thanks. So let's look at our score function gradient estimator again in the Gaussian case. So in the Gaussian case, so we have grad log probability times f of x. So here's where we're just computing a gradient of expectation of f of x. And so this is our estimator. And in the Gaussian case, we're going to get something like, we're going to get x minus our mean times f of x. And then we're divided by standard deviation squared. So the problem here is that we have this factor 1 over. So the question is what's going to happen as sigma goes to 0? So we're wondering if the variance goes to 0, does our estimator get like any worse, or what happens to it? And if you look at this expression, let's see. So what's the argument why the variance will go to infinity? So if we look at the finite difference case, then what we have is if we take the function value, let's see. OK, well, if we rewrite it like x equals mean plus sigma times our random variable, where z is from normal 0, 1, then we end up we have sigma z over sigma squared times f of mu plus sigma z. So then we just have z over sigma times f of mu plus sigma z. And z is, we're not changing the size of z. Z is always normal 0, 1. So if you just look at, and our variance is going to depend on this expression squared. So our variance is going to be gradient estimator squared. So it's going to be like, it's going to be expectation of z over sigma times f of mu plus sigma z minus our true gradient squared. So this is going to be our variance. And as you can see, as sigma goes to 0, this term is going to get bigger and bigger. So, I mean, is that clear? So, so the variance, that means the variance goes to infinity as sigma goes to 0. So that's not so good. It's kind of like when you do finite differences and you have noise, you have some sorts of noise in your function values. Then you want to do a big finite difference instead of a small finite difference. Because if you try to do a small finite difference, the noise is going to dominate. Like, let's say here's your function, okay, if the function doesn't have any noise, or if there's no noise when you evaluate the function, then you can use a small finite difference perfectly well. But now let's say you add a little bit of noise to both, to both of the points that you're taking the difference between, then you're going to mostly be seeing the noise, not the actual difference in function values. So in finite differences, that would be like if we're taking f of theta z, well, let's say f of theta plus, what were we using? We were using sigma. F of theta plus sigma z minus f of theta minus sigma z over 2 sigma. So this is our finite difference gradient estimator. If we use the same value z on both sides, then we're OK, because it's like we're fixing the noise between both of our function evaluations. So we're still going to approximately estimate the gradient for that particular value of z. But if we have 2 different values of z here, so let's call this one z1 and z2, then if sigma goes to 0, then our first argument is going to be basically the same on both sides, but our second argument is going to be different. So all we're measuring is the noise, which is we're just measuring the effect of taking 2 different samples of the noise. So I guess my point is just that the issue with the score function gradient estimator is kind of the same as when you're trying to do finite differences and you drive the difference to 0. Okay, but the SVG gradient estimator is fine as sigma goes to 0. So here, the limit is perfectly well defined as the noise on the policy goes to 0. Because here we're just taking the gradient of the Q function. So we don't care we don't care how we're not taking the difference between 2 different values. We're just looking at how the gradient of the derivative of the Q function with respect to the action. So the only problem if you just drive the noise to 0 is there's no exploration. If you just have a deterministic policy, so then you might not discover some of the good behaviors. But the solution that's proposed in this paper by Silver et al. Is you add noise to the policy. But okay, so if you add noise to the policy, then it would seem that now we're back to having a stochastic policy. And should we learn the Q function for our stochastic policy or for our noise-free policy? So what they propose in the paper is that you use TD0 to estimate the Q function. So you can do an off-policy estimate of the Q function. So you can estimate the Q function of the noiseless policy and use that to compute the policy gradient estimator. You can use that to estimate the policy gradient for the noiseless policy, even though you're sampling from the noisy policy. So it's like a kind of off-policy sampling. And then your policy gradient is a little biased, even if you have the perfect Q function. But it's only biased because your state distribution is off, because you're sampling states from your noisy policy rather than from your noiseless policy. You get the right gradient at every single individual state. So if you have an unlimited capacity of your Q function, then so that means if independent states are going to learn, if the states are going to learn independently of each other, then you're going to learn the correct. You're going to learn the correct, get the correct policy gradient at every state. That's a little bit vague, but the point is that if you don't have to worry about where you're weighting the state space, then gradient estimator is going to do the right thing. Because if you have like a limited capacity in general, then it's going to matter how much you weight different samples. But if you have unlimited capacity, then it shouldn't matter. OK, so then there was another follow-up paper by Lillicrap and others where they called this algorithm deep deterministic policy gradient. And they incorporated some ideas from DQN to increase the stability, because the previous version of the algorithm wasn't very stable, because presumably because the bias, well, first of all, you're trying to estimate a Q function using TD0, and that's hard with function approximation. And second, you're getting pretty biased policy gradient estimates. So then you also don't necessarily see very monotonic behavior. So they introduced some ideas from DQN to improve the stability and the performance. So they, instead of using the latest Q function to update the policy, they used a lagged version of the Q function, which is kind of analogous to using a target network in DQN. And so they actually used the, so they used the lagged version of Q for updating Q, not for updating the policy. And I think they also used a lagged version of the policy that they plugged into the Q function to do the backup. So what they do is, so the pseudocode is basically you collect some data from your policy, you add the data to your replay buffer, sample a mini batch, update the policy using the Q function to define the gradient, and you update the Q function using a squared error kind of loss. And they used TD0 so that they could get off-policy estimates of the Q function. And they applied it to some 2D robotics tasks and some simple 3D robotics tasks and a driving task with pixel input. So it's pretty cool that you can do a task with pixel input using this same method. So now just to review what we have so far, we have two different kinds of policy gradient estimator. So we have the reinforce or score function estimator, where we have grad log probability times the advantage function. And what you can do is you can learn the Q function or the value function to do variance reduction and estimate the advantage function. And we also have these pathwise derivative estimators, which involve differentiating through the actions, or considering how the actions are going to change as a function of the policy parameters, and in turn how that's going to either change the value function or the whole trajectory. So that's why you can call them pathwise derivative, because you're looking at how the whole path is going to change instead of just the probabilities. So we have the SVG0 or DDPG, where we're looking at the derivative of the Q function with respect to the action. Then we have SVG1, where, that should say Q of the, there's just a Q missing. Oh, no, actually, no, there's nothing missing, sorry. SVG1, you differentiate reward plus next value, where the S prime is a function. You also learn the dynamics model there, so you can see how S prime is going to change. And SVG infinity, you look at the whole returns, and you consider the returns to be a deterministic function of everything, of your actions, and well, you consider it to be a deterministic function of your policy parameter and some noise that you sampled. And you differentiate through that whole process like it's an RNN, and that gives you another policy gradient estimate. And in general, the pathwise derivative methods are more sample efficient when they work, because you're not trying to compute finite differences with noisy functions. But they work less generally because they generally have some bias because your dynamics model is wrong and your value function is wrong. But these methods, there's no way of getting rid of the bias. So with score function estimate methods, we can get rid of the bias by just using the returns minus baseline. So if we just take returns minus baseline, that gives us an unbiased estimator. And then we can introduce bias. As we showed in the last class, we can make a bias variance trade-off. And we can try to choose a appropriate level of bias so that our gradient is still pointing in the right direction. But with these pathwise derivative methods, there's no way to totally get rid of the bias. So that's what the big problem is. And the other issue with them is they depend on, we're fitting the Q function and the value function using squared error. So we're writing down the squared error of the Q function and fitting it that way. But that's not necessarily what matters for getting, low bias or low variance for our estimator. So it's not, because what we're actually taking is the derivative of the value function. So in SVG0 or SVG1, we're taking the gradient of the value function. But when we fit the value function, we're not looking at the gradient at all. So there's kind of a mismatch between the criteria we're using to learn the value function and the way we're actually using it. There's no guarantee that if our value function is accurate to within epsilon in terms of squared error, that our policy gradient is going to be accurate to within epsilon, or that it's going to have low variance. To see that, well, actually, you can see that it might have really high variance even if we have a really accurate value function. Actually, I want to make another point about the pathwise derivative estimator. So I said that the pathwise derivative estimator is better most of the time because you're actually measuring the derivative. But let's try to think of a case where it's not going to be very good. So let's think about let's just draw a little picture that illustrates what the pathwise derivative estimator is doing. So let's say here's f of x, and then here's our probability distribution, p of x, and our mean is theta. And we want to figure out how the expectation of f of x is going to change when we move our mean around. So let's say we get a sample. Then the pathwise derivative is just looking at what's the slope at our sample point. So that's going to be really, really good if the slope is basically fixed over the whole distribution. I mean, in fact, it's going to have zero variance. If the slope is fixed over the whole support of the distribution, then we're going to get zero variance because we're always going to get the right answer. OK, but now let's say our function f of x looks like this. Then we can make the estimator have arbitrarily high variance by making the function more and more wiggly. So this is like a pathological case where the pathwise derivative estimator is going to be bad. It remains to be seen in practice whether this is actually the case for the functions we care about. On the other hand, it's hard to have intuition about whether this is the right picture or the smooth function is the right picture when you have really high dimensional functions. So anyway, that's just showing you that you might have an accurate Q function, but it might be bad for gradient estimation, because or you might have a reasonably accurate dynamics model, but it might be really bad because it might have all these wiggles on it. I don't think that's going to happen in practice, but what does happen in practice is when you try to apply one of these methods, and you can make certain choices that'll affect the smoothness of your value function. And sometimes you end up with a less accurate value function. You increase the smoothness, and that makes it less accurate, but your learning works better. So that's something you find in practice. You can do an experiment where you use, say, radial basis functions, and you can control the fall off of the basis functions, like what the width of the basis functions is. And you find that there's a certain sweet spot for how wide the basis function should be. And this does not necessarily correspond to getting the best accuracy of the value function. It turns out that smoothness also helps. And so that means that we're missing something if our criteria for the learning the value function does not exactly match what matters for improving the policy. So now it's also worth just going back and comparing the policy gradient methods, which we've been talking about for the past couple weeks, to the Q function methods, which we were talking about before that. So previously we were talking about deep Q learning, and we also mentioned that there's SARSA, where you just estimate the value function of the current policy. So informally, I'll just say a little bit about what are some of the qualitative differences, or why would you want to use one class of methods rather than the other. So the Q function regression methods are usually more sample efficient when they work, but they don't work as generally. So for example, on Atari, the best results that have been published in terms of learning fast in a small number of samples are obtained with these methods that learn a Q function and do lots of experience replay or lots of off-policy learning. But on the other hand, Q function, there are a lot of problems where you can't really apply, where Q learning hasn't been shown to work well. But I'm pretty sure for every problem that Q learning has been shown to work well, people have also been able to use policy gradients. At least all of the well-known benchmark problems like Atari and some of the continuous control tasks that people have looked at. So I would say that policy gradient methods are easier to debug and understand. You have a lot of good diagnostics that you can print out. So you don't have to deal with the long burn-in period at the beginning of optimization. So in your homework assignment, you're trying to, well, in your previous homework assignment, you used DQN to learn a policy for the Atari game of Pong. And it didn't show any signs of life for a long time, for something like 1 million samples. Is that right? About 1 million? Yeah. So so you don't have, so that's kind of makes it hard to tune these algorithms, because if it's not learning anything for a while, it's hard to see if your algorithm is wrong, or if your implementation is wrong, or if it's just too hard, and it's so you don't have to deal with this burn-in period for policy gradient methods to the same extent. So usually, if it doesn't start learning, it's not going to learn. When it's working, the performance should be monotonically increasing. So you don't expect to see like really big fluctuations in performance. You should see it kind of just go up monotonically. And if it doesn't, you might be using too large of a step size. And yeah, you have these. You can look at the KL of the policy and try to make sure. So in your homework assignment, the code prints out what's the KL between the old policy and the new policy. That's a useful diagnostic to make sure your optimization is, you're not taking too big steps. And you can look at how much of the variance is explained by the baseline, so you know if the baseline is helping or not. Whereas in Q learning, your Q function is supposed to approximate the returns well, but in practice, it's usually a pretty inaccurate approximation. So there's not really a good diagnostic that'll tell you that you're not fitting it properly. On the other hand, there's some big advantages of the Q function regression methods. So they're more compatible with exploration and off-policy learning. Actually, I guess this isn't strictly something that has to do with whether you're learning a Q function or a policy, but it has to do with whether you're using TD0, whether you're using, that means a one-step estimator of the advantage and returns, or whether you're using TD lambda, or you're using an n-step estimator of the advantage and returns. So if you're using the one-step estimator, then you can do proper estimates off policy. Whereas if you're using the n-step estimator, you can't really get a proper off-policy estimate. Though I'll mention on the next slide that there's some recent methods that try to address that. When people use policy gradient methods, they usually look at longer look-aheads, because you try to get low variance on your policy gradient estimates. And to do that, you need to use longer sequences. But with you could also do a TD0 type estimator for policy gradients, but it usually has high bias, and people don't find it to work very well in practice. That's like advantage 1 from the previous class, or that's like the one-step estimator of the advantage function, where you use reward plus next value minus current value. So you can do that kind of thing, and you could make this, if you use a Q function, you could get an off policy. You could do this off policy, but in practice, this hasn't been found to be that effective. But anyway, so when you use off-policy methods, they're more compatible with exploration and with reusing all data, which increases sample efficiency. So policy gradient methods are more compatible with using recurrence, just because with Q-learning, I mean, the most sample efficient form of the Q-learning algorithms is DQN, which uses this replay buffer. And to use a recurrent policy, you have this hidden state which gets updated over multiple time steps. So you would have to sample, to train a recurrent Q function, you would have to sample a chunk of time steps that are contiguous in time, because you want to look at how this hidden state evolves over time. And this ends up just hurting slowing down optimization. If you can't just IID sample your time steps, you have to sample a chunk of contiguous time steps, so that it ends up, people haven't gotten that great results using Q-learning with recurrent policies. In general, this is just an empirical statement. This isn't a theoretical statement, and it might change really easily. But policy gradient methods are really straightforward to use with recurrent policies without changing anything about the algorithm. And Q function, so some people think the Q-learning can't be used with continuous action spaces, but it can pretty straightforwardly. You have to choose a different kind of parameterization of the Q function than we used with DQN. So instead of outputting a Q value for every action, you're going to output some other functional form, or the parameters of some quadratic or some, I don't know, there are different choices. But this can be done, but in practice, it seems to give worse final performance than the policy gradient methods. So people haven't been able to solve some of the harder benchmark problems using Q-learning, using this type of method. So I think it's only been successful at solving some of the simpler problems. Let's see. So there have been some nice recent papers connecting policy gradient methods and Q function regression methods, because these are actually very similar. So here are just a few of the recent papers. So I mean, this idea has been, there have been a lot of older papers that also made this point, but it's sort of come to prominence recently because these are two really popular classes of methods for deep reinforcement learning. So it's pretty useful to know that there's actually some mathematical similarity between them. So these are just some papers that do that. There's actually a really nice idea that I didn't get a chance to talk about in this class, but if you want to, you can check out this paper, Q of lambda with off-policy corrections, which I think is a pretty, like a readable description of the idea. And the idea is that you can adjust the returns if you have a Q function. So we talked about, last class we talked about using a value function in the future to cap off the returns. So you're using a value function in the future to reduce variance at the cost of bias. But we were just talking about using state value functions. And it turns out that you can use the Q function in a nice way to do some variance reduction with the returns. So the idea was, well, I don't know, it's been proposed in a couple of different papers. So it was used in, let's see, oh yeah, this paper, sample efficient actor critic with experience replay, used the idea. I don't know if it actually, they didn't, I don't know if they did that much in the way of like teasing out the effect of this change to the algorithm versus some other changes, but they used this idea, this variance reduction idea to get a better policy gradient estimate. So that's one nice idea. So they use experience I guess the way they're connecting policy gradients and Q function regression here is just that they're using experience replay to learn a Q function and then plug that into a policy gradient method. Let's see. There's another couple of recent papers on this idea. And actually, there's just a really simple calculation that you can do to see sort of why there's a similarity between policy gradient methods and Q function regression methods. So I'll just show really informally what the similarity is. So in a Q function regression method, you have some kind of squared error loss, like Q of SA minus some target Q value. So here's your loss, and then you're differentiating it. Let's decompose this a little bit, though, and let's say, so remember when we mentioned the dueling networks idea, that's just that you parameterize the Q function as a sum of a advantage part and a state value part. This parameterization helps you a little bit. So you take, let's take the gradient of this with respect to theta, and let's ignore the value function part and just look at the advantage part. So we get gradient of the advantage function times your well, I guess we're let's see. OK, yeah. So we have advantage plus value minus your. Actually, let me call this R hat instead of Q hat because this is the returns. So this is your loss function gradient, and let's say we want to do gradient ascent. So then we're going to take a step that because we want to do gradient descent on this one, but let's say we want to do gradient ascent. Then we want to look at the negative of this gradient. So we're going to have something like grad of advantage times reward hat minus value plus advantage. So, okay, so that's okay. So that's what we get for the Q function regression case, and then let's look at. Okay, so now let's say that the if we have a policy that's defined, let's define our policy as the advantage function, exponential of the advantage function, divided by some kind of normalizing constant, which is different at every state. Then we end up with, so we have log probability is advantage minus log z. So when we look, so that means the gradient of the advantage. Okay, so you can do this calculation more precisely, but I'm just trying to show you the gist of it. So you see that there's if we were to plug in the if we were to take the gradient and we write the gradient of the advantage with respect to the gradient of the policy that we're defining this way, then we end up with something like grad log probability of A given S, and then minus what is it, grad log Z times reward minus this expression. So you can see that it's kind of like grad log probability times advantage, and but it's okay. So that's, you can see that there's sort of a connection there, and but you can actually make this more precise and find that there's a more precise equivalence between the policy gradient and the gradient in the Q function regression. I mean, if you look at the, let's see, yeah, it turns out that this advantage term you get from if you have an entropy bonus and you add that to your policy gradient, it gives you a term that looks like this, because in your normal policy gradient estimator, you have grad log probability times your returns minus your state value function. And but here we have an extra term, which is like the advantage, or this is like the log probability. And if you so it turns out that there's a connection between when you do the policy gradient with the when you do the policy gradient with an entropy bonus, and when you do the gradient of the regression loss. So you can find that calculation is in the PGQ paper, and actually my colleague and I have another version of this calculation that we have a paper on this that is coming out soon. Let's see. Oh yeah. So okay. So that's all for my material today. Does anyone have questions? All right. So see you next Monday.